Hi, hello there. Welcome to Single Area Ospf version 2 configuration. Now that you know about Single Area Ospf version 2, you can probably think of all the ways it could benefit your own network. So, as a state link protocol, OSPF is designed to not only find the fastest available route, it is designed to create fast available route. So if you prefer a bit of more control over some areas of your network, OSPF gives you several ways to manually override the Bdr election process and create your own preferred routes. So with OSPF, your network can combine the automated process with your own choices to make a network that you could troubleshoot in your sleep. All right. So, you want to learn about this. So let's get it on. All right. So for the module objectives, so this topic or video lecture covers the single area OSPF version 2 configuration. So the objective would be at the end of this video lecture, so you should be able to implement a single area OSPF version 2 in both point-to-point and broadcast multi-access network. So subtopics included on this video lectures are Ospf Router Id, the point-to-point OSPF networks, the multi-access OSPF networks, modify single area OSPF version 2, the default route propagation, and verify single area OSPF version 2. All right, so let's start with the first section. So let's talk about the Ospf Router ID. Okay, so this would be our OSPF reference topology. So this will be utilized throughout the discussion. Okay, so to get started, this topic discusses the foundation of which OSPF bases its entire process, the Ospf Router ID. So the figure here shows the topology used for configuring OSPF version 2 in this module. So the routers in the topology have a starting configuration, including interface addresses. There is currently no static routing or dynamic routing configured on any of these routers. So all interfaces on R1, R2, and R3, except the loopback on R2, are within the OSPF backbone. Okay? So when you say backbone, we're talking about area 0. So the ISP router is used as a gateway to the internet of the routing domain. Okay, so take note that on this topology, the loopback interface is used to simulate a WAN, okay, or a WAN link to the internet and a LAN connected to each router. So this is done to allow this topology to be duplicated for demonstration purposes on routers that only have 2 gigabit Ethernet interfaces. Okay, so router configuration mode for OSPF. So OSPF version 2 is enabled using the router OSPF process ID global configuration mode command. So as shown in here, so this is for R1 here. Okay, so the process ID value represents the number between 1 to 65,535. So you can use any number within that range and is selected by the network administrator. So the process ID is locally significant, which means that it does not have to be the same value on the other OSPF routers to establish adjacencies with those neighbors. So it is considered best practice to use the same process ID on all the OSPF routers. Okay, now after entering the router OSPF process ID command as shown here, so the router enters router configuration mode. So as indicated by, you've got R1 here, config, and then you've got the router. Okay, so this would be the prompt. So enter a question mark. Okay, so to view all the commands available in this mode. So the list of commands shown here has been altered to display only the commands that are relevant to this module. Right? Okay, so let's talk about the router ID. So an Ospf Router ID is a 32-bit represented as an IPv4 address. So the router ID is used to uniquely identify an Ospf router. So all Ospf packets include the router ID of the originating router. So every router requires a router ID to participate in an Ospf domain. So the router ID can be defined by an administrator or automatically assigned by the router. So the router ID is used by an Ospf-enabled router to do the following. First, participate in the synchronization of the Ospf databases. So during the exchange state, the router with the highest router ID will send their database description, all right, or the database descriptor or DBD packets first. Okay, so next would be participate in the election of the designated router or DR. So in a multi-access LAN environment, the router with the highest router ID is elected the DR. So the routing device with the second highest router ID is elected as the backup designated router or Bdr. So the router that is not considered a DR or Bdr is known to be Drbddrs. Okay, so take note that Dr and Vdr election is discussed in more detail later in this module. Okay, so how about the router ID order of precedence? Okay, so but how does this router ID determine the router ID? Okay, so as illustrated in the figure, okay, so Cisco routers derived the router ID based on one of the three criteria. So that is in the following preferential order. So first, the router ID is explicitly configured using the Ospf Router Id RID router configuration mode command. So the RID value is any 32-bit value expressed as an IPv4 address. So this is the recommendation method to assign a router ID. Okay. Second, if the router ID is not explicitly configured, the router chooses the highest IPv4 address of any configured loopback interfaces. Okay, so this is the next best alternative to assigning a router ID. Okay, so the third one would be if no loopback interfaces are configured, then the router chooses the highest active IPv4 address of any of its physical interfaces. All right, so this is the least recommended method because it makes it more difficult for administrators to distinguish between specific routers. Now, as shown here in the diagram, so this summarizes what I have discussed. Okay, so router ID explicitly configured. If yes, that would be used as a router ID. So if not, then the router will look for the loopback if the administrator has configured any loopback on the router, and that would be used as the router ID. Now, assuming if you have multiple loopback configured in the router, so the router will choose the highest IP address assigned to the loopback. All right. Now, if in case you did not define the router ID, okay, nor the loopback interfaces, then the router will choose the highest active IP address on the interface of the router. Okay, so there is no instance that the router won't have a router ID. Okay, next, so how do we configure a loopback interface as the router ID? So in the reference topology presented earlier, only the physical interfaces are configured and active. So the loopback interfaces have not been configured. So when OSPF routing is enabled on the routers would pick the following highest active configured IPv4 address as the router ID. Okay, So if we are going to go back to our topology, we'll have R1, R2, and R3 there. Okay. So note that OSPF does not need to be enabled on an interface for that interface to be chosen as the router ID. Okay. So instead of relying on a physical interface, the router ID can be assigned to a loopback interface. So typically, the IPv4 address of this type of loopback interface should be configured using a 32-bit subnet mask. Okay, so that is 255.255.255.255. So this effectively creates a host route. So a 32-bit host route would not get advertised as a route to other OSPF routers. Okay, now the example shows how to configure a loopback interface on R1. Okay, so interface loopback number. Okay, so assuming that the router ID was not explicitly configured or previously learned, R1 will use the IPv4 address 1.1.1.1 as its router ID. All right, so assume R1 has not yet learned a router ID. Right, so you can verify what the router ID is of a router using the command show IP protocols. So in there, you can see the router ID. And in this case, so we did not configure manually or explicitly a router ID. Then after we configured a loopback, that would be fetched as a router ID. Okay. Next. So in the figure, so the topology has been updated to show the router ID for each of the router. So R1 uses 1.1.1. Okay. So R2 uses 2.2.2 and R3 uses 3.3.3. Now we use the router ID RID router configuration mode command to manually assign a router ID. In this example, the router ID 1.1.1.1 is assigned to R1. So we use the command show IP protocols command to verify the router ID for each of the router here. Okay, so like what you see here, show IP protocols. So router ID is 1.1.1 for R1. Okay, so after we explicitly define it as router ID 1.1.1.1. All right. Okay, so how do we modify a router ID? So after a router selects a router ID, an active OSPF router does not allow the router ID to be changed until the router is reloaded or the OSPF process is reset. Okay, now in the example here for R1, the configured router ID has been removed and the router is reloaded. All right. So how do we reload the router? So you could use the clear IP OSPF process. Okay, reset all OSPF configurations or processes. Yes. Okay, and then that's it. All right. So notice that the current router ID is 10. Okay, .10.1.1, which is the loopback 0 IP address. All right. So the router ID should then be 1.1.1.1. So therefore, R1 is configured with the command router ID, okay, 1.1.1.1. Now notice how an informational message appears starting that the OSPF process must be cleared or that the router must be reloaded. All right. So the reason is because R1 already has adjacencies with other neighbors using the router ID 10.10.1.1. So those adjacencies must be renegotiated using the new router ID with 1.1.1.1. Okay. So what we're going to do is to use the clear IP OSPF process command to reset the adjacencies. Now you can then verify the R1 is using the new router ID command with the show IP protocols command pipeline. Okay, so that is to simplify the output, right? to display only the router ID section. Okay, so clearing the OSPF process is the preferred method to reset the router ID. Right, so take note that the router ID command is the preferred method. However, some older versions of the iOS do not recognize the router ID command. Okay, so aside from the clear IP OSPF process, okay, so after all the clearing of the OSPF process and it doesn't take effect on the router, so maybe you could try saving your configuration and restarting or resetting the router itself. Okay, now let's move on to the next section. So the next section talks about point-to-point OSPF networks. Okay, so let's talk about the network command syntax. Okay, so one type of network that uses OSPF is the point-to-point network. So you can specify the interfaces that belongs to a point-to-point network by configuring the network command. So you can also configure OSPF directly on the interface with the IP OSPF command, as you will see later. Okay, so both commands are used to determine which interfaces participate in the routing process for an OSPF version 2 area. So the basic syntax for the network command is as follows. Okay, so you've got router, config router, so you've got network, network address, wildcard mask, area, and the area ID. Okay, so the network address wildcard mask syntax is used to enable OSPF on interfaces. So any interfaces on the router that match the network address in the network command are enabled to send and receive OSPF packets. So the area ID syntax refers to the OSPF area. So when configuring a single area OSPF version 2, the network command must be configured with the same area ID value on all routers. Okay, so although any area ID can be used, it is a good practice to use an area ID of 0 with single area OSPF version 2. Okay, so this is in convention, okay, making it easier if the network is later altered to support the multi-area OSPF version 2. Alright, so how about the wildcard mask? Okay, so the wildcard mask is typically an inverse of the subnet mask configured on the interface. So in a subnet mask, binary 1 is equal to a match and binary 0 is not a match. So in a wildcard mask, the reverse is true as shown here. Alright, so if the subnet mask is 255.255.255, okay, so you have to subtract it from 255.255.255.255, okay, so the wildcard mask would be 0.0.0.0. It should be 0. Okay, so the wildcard mask bit 0 matches the corresponding bit value in the address, and the wildcard mask bit 1 ignores the corresponding bit value in the address. So the easiest method for calculating a wildcard mask is to subtract the subnet or the network subnet mask from 255.255.255.255. Okay, so as shown for /24 and /26 subnet masks in the figure. All right, so we have here some correction on this PowerPoint presentation. So if it is /26, okay, so subnet mask for /26 would be 255.255.255.192. All right, so subtracting it from 255.255.255.255. All right, so let's do some adjustment on this PowerPoint here. Okay, so take note, if it is /24, That's 255.255.255 dot. This should be 0 here. All right. So subtracting it, so therefore the wildcard mask for /24 would be 0.0.0.255 there. All right. Now for /26, this should be 192 here. All right. So it should be 192. Okay, so just change that to 192 here. That's /26. Okay. So that would be, okay, subtracting it from 255.255.255. So that would be 0.0.0. Okay. Dot. All right. So it should be dot 63. Okay. That is for /26. Right? Okay, so let's configure OSPF using the network command. So within the routing configuration mode, there are two types to identify the interfaces that will participate in the OSPF version 2 routing process. So the figure shows the reference topology here. Okay. Now in the first example, the wildcard mask identifies the interface based on the network address. So any active interface that is configured with an IPv4 address belonging to the network will participate in the OSPF version 2 routing process. Okay. Now in here, referring to this topology or given topology, and our reference is on R1. All right. Now on R1, so of course, we need to start with router OSPF. Okay, so 10 network 10.10.1.0 0.0.0.255 area 0. So this is area 0 here. So all of those should be area 0. Okay. Now in defining the OSPF, so we care only about the directly connected networks. And if we are going to evaluate R1, okay, so look at R1 here. So there are 3 networks connected to it. So this would be the first network, this would be the second network, and this would be the third network here. Okay, so the first network would be 10.10.1.0, which is the loopback 0 here. Okay, next would be 10.1.1.4, which is the network between R1 and R2, and 10.1.1.12, which is the network between R1 and R3. All right, so take note that the loopback network, which is 10.1.1 or 10.10.1.0 is /24 here. So therefore, the wildcard mask would be the /24. So that's 255.255.255.255 minus 255.255.255.0. So that makes it 0.0.0.255 here. Right? Now, this 2 here, which is between R1 and R2, right? And of course, also between R1 and R3 here, these are both /30. Okay? And that means that would be 255, all right? So let me just write it here. 255. Okay, so bear with my handwriting there. 255. Okay, so I have a hard time using the mouse. That /30 is 252. Okay, so that means when we subtract it from 255, okay, that 255, okay, that 255, this would yield to, of course, you've got 0, that's 0, that's 0, that 3. So which are the wildcard masks here. Okay, so take note that some iOS versions allow the subnet mask to be entered instead of the wildcard mask. So the iOS then converts the subnet mask to the wildcard mask format. All right. Okay, so as an alternative, okay, so the second example shows how OSPF version 2 can be enabled by specifying the exact interface IPv4 address using a quad 0 wildcard mask. Okay, so entering network 10115, right? So you've got here 0.0.0.0 area 0 on R1, which tells the router to enable interface gigabit Ethernet 0/0/0 for the routing process. So as a result, the OSPF version 2 process will advertise the network that is on this interface 10.1.1.4/30. All right. Now, the advantage of specifying the interface is that the wildcard mask calculation is not necessary. So notice that in all cases, the area argument specifies area 0. So if you will observe here, okay, you've got quad 0 there. So that means it is more specific, specifying the exact interface IPv4 address. Okay? All right. So next would be configure OSPF using the IP OSPF command. Okay? Now, you can also configure OSPF directly on the interface instead of using the network command. So to configure OSPF directly on the interface, we use the IP OSPF interface configuration mode command. Okay? So the syntax is given here. All right? So router, okay, config if, so IP OSPF, process ID, area, and then you've got an area ID. Now for R1, remove the network commands by using the no form of the network commands. Something like no network 10.10.10 or 10.10.11, okay, 0.0.0.0 area 0. No network 10.1.1.5, and then no network 10.1.1.14. Okay, and then go to each interface and configure IP OSPF command as shown here. So IP OSPF 10 area 0. Okay, so that is for interface gigabit Ethernet 0.0.0.0. Interface gigabit 0.0.1. So in there you configured IP OSPF 10 area 0. But then most of the time we are using the network command. All right, so but then it's up to you. You can use this as an alternative of doing the configuration. Okay, for loopback 0, so IP OSPF 10 area 0. So it has the same effect. All right. Okay. Next would be, let's talk about passive interface. Okay. So by default, OSPF messages are forwarded out all OSPF enabled interfaces. So however, these messages really only need to be sent out interfaces that are connecting to other OSPF enabled routers. Now, refer to the topology in the figure presented earlier. OSPF version 2 messages are forwarded out 3 loopback interfaces, even though no OSPF version 2 neighbor exists on this simulated LANs. So, in a production network, these loopbacks would be physical interfaces to networks with users and traffic. Okay, sending out unneeded messages on the LAN affects the network in 3 ways as follows. Okay, so first, you've got inefficient, right, bandwidth. So available bandwidth is consumed transporting unnecessary messages. Next would be inefficient use of resources. Okay, so where's my pointer? Right, so this is the second one, inefficient use of resources. So all devices on the LAN must process and eventually discard the message. So next would be increased security risk. So without additional OSPF security configurations, okay, so OSPF messages can be intercepted with packet sniffing software. So routing updates can be modified and sent back to the router, corrupting the routing table with false metric that misdirect traffic. Okay? All right. So how do we configure a passive interface? So we use the passive interface, okay, router configuration mode command to prevent transmission of routing messages through a router interface. So but still allow that network to be advertised to the other routers. So the configuration example identifies the R1 loopback, okay, the R1 loopback 0 as passive. Okay, so in here, so router OSPF10 passive interface loopback 0. So we are going to place loopback 0 to a passive interface, and therefore it will not receive any updates that is intended only for devices that is configured with OSPF. Okay, so usually, okay, so this passive interface command is being used if you are connecting a switch or a computer connected to that port. But basically, if you are connecting router, okay, so to another router, we do not execute passive interface on that interface because it will not forward or it will not send or receive updates, okay, so for OSPF. All right. Now, after this, you could use the command show IP protocols, okay. So this is used to verify that the loopback 0 interface is listed as passive here. So below here, so take note that passive interfaces, they're listed loopback 0. All right. Okay, so OSPF point-to-point networks. So by default, Cisco routers elect a Dr and Vdr on Ethernet interfaces. So even if there is only one other device on the link. So you can verify this with a show IP OSPF interface command. So as shown here in the example, for G00 of R1. Okay, so as you can see here, so show IP OSPF interface G00, 0. So network type is broadcast. So that means it is on the multi-access network, okay, or an Ethernet interface, right? So also you can see here the designated router ID is 2.2.2, okay, and the backup designated router ID on that network would be 1.1.1. All right, so R1 is the Bdr and R2 is the Dr. Okay, so that is based on the output that we have earlier. Now, the Drbddr election process is unnecessary as there can only be two routers on the point-to-point network between R1 and R2. So notice in the output that the router has designated the network type as broadcast. Okay, so to change this to a point-to-point network, we use the interface configuration command IPOSPF network point-to-point on all interfaces where you want to disable the Drbddr election process. Right? So the example below or in here shows this configuration for R1. So the OSPF neighbor adjacency status will go down for a few milliseconds. All right? So as you can see here, show IP OSPF interface gigabit Ethernet 000. Right? So after some time, okay, after a few milliseconds, notice that the gigabit Ethernet 000 interface now lists the network as type point-to-point, and that there is no Dr or Bdr on the link. Okay? So let me reiterate that Dr and Bdr is applicable only when you connect your router to a switch, right? So wherein multiple routers are connected to it. Okay, so loopbacks and point-to-point networks. So we use loopbacks to provide additional interfaces for a variety of purposes. In this case, we are using loopbacks to simulate more networks than the equipment can support. So by default, loopback interfaces are advertised as /32 host routes. Okay, /32 host routes. Now, for example, R1 would advertise 10.10.1.0/24 network as 10.10.1.1/32, both to R2 and R3. Okay. Now, to simulate a real LAN, the Loopback 0 interface is configured as point-to-point network so that R1 will advertise the full 10.10.1.0 network to R2 and R3. Right? So if you can see here, so interface Loopback 0, IP OSPF network point-to-point. Okay? Now, R2 receives the more accurate simulated LAN network address of 10.10.1.0/24. Right? So show IP route here. So include 10.10.1. So I'll have here 10.10.1.0/24 is in there. All right. So next, let's go to the next section, multi-access OSPF networks. Okay. All right. So on this section, let's talk about the OSPF network types. So another type of network that uses OSPF is the multi-access OSPF network. So multi-access OSPF network are unique in that one router controls the distribution of LSAs. So the router that is elected for this role should be determined by the network administrator through proper configuration. So OSPF may include additional processes depending on the type of network. So the previous topology used point-to-point links between the routers. So however, routers can be connected to the same switch to form a multi-access network. So as shown here in the figure, so we have connected 4 routers to a single switch. So Ethernet LANs are the most common example of broadcast multi-access network. So in a broadcast multi-access network or broadcast networks, all devices on the network see all broadcast and multicast frame. All right? Okay, so next would be the OSPF designated router. So recall that in multi-access network, OSPF elects a DR and Bdr as a solution to manage the number of adjacencies and flooding of link state advertisements or LSAs. So the DR is responsible for collecting and distributing LSAs sent and received. So the DR uses the multicast IPv4 address as mentioned in the previous video lecture. That would be 224.0.0.5, which is meant for all the OSPF routers. Okay? So a Bdr is also elected in case that the DR fails. Now, the Bdr listens passively and maintains a relationship with all the routers. So if the DR stops producing hello packets, the DR promotes itself and assumes the role of the designated router or the DR. Now, all other routers become a Drbddr. So a router that is neither the DR nor the Bdr. So Drbddrs use multi-access address 224.0.0.6. So all designated routers to send OSPF packets to the DR and Bdr. So take note, only the DR and Bdr listen for 224.0.0.6. All right. So what is the role of the DR or designated router? So in the figure here, R1, R5, R4 are Drbddrs. All right. And the Bdr process the LSA sent by R1 using multicast IPv4 address 224.0.0.6. Now the DR then sends out the LSA, okay, to all the OSPF routers using the multicast IPv4 address 224005. Right? So the DR is responsible for sending all the LSAs to all the routers here. Okay? So in that sense, it eliminated the possibility of a flooded network. Okay? So OSPF multi-access reference topology. So let's use this in a multi-access topology shown in the figure. Okay? So there are 3 routers interconnected over a common Ethernet multi-access network 192.168.1.0. Okay, so that is /24. Right? Now, each router is configured with the indicated IPv4 address on the gigabit Ethernet 000 interface. Because the routers are connected over a common multi-access network, OSPF has automatically elected a DR and a Bdr. Now, in this example, R3 has been elected as the DR. Why? Because each router ID is 3.3.3.3. Okay? So, the highest router ID, okay, so in this case, so 3.3.3.3, which is the highest in this network, right? So it will be chosen as the DR. Okay? So R2 is the Bdr because it has the second highest router ID in the network, which is 2.2.2.2. Right? And therefore, R1 here is a Drbddr. Right? Okay, so how do we verify OSPF router roles? So to verify the roles of the OSPF version 2 router, we use the command show IP OSPF interface. Right? Now, for instance, we have here our consideration. R1 is the Drbddr, right? So from the previous slide, R1 was a Drbddr. So the output generated by R1 confirms that the following. First, R1 is not the DR or Bdr, but it is a Drbddr with a default priority of 1. Right? So take note, state Drbddr, priority 1. Okay? So next would be the DR is R3. Okay, so take a look at this. The designated router is R3, having a router ID of 3.3.3.3. And that is connected via interface address 192.168.1.3. So while the Bdr is R2, okay, so with router ID 2.2.2.2 at IP address 192.168.1.2. Okay? Next, R1 has 2 adjacencies, one with the Bdr and one with the DR. Okay, so it's adjacencies. Take a look at this. Adjacent with neighbor 2.2.2.2, which is the Bdr, and it is also adjacent with 3.3.3.3, which is the designated router. All right, so that's how to verify OSPF router roles. Okay, so let's check the R2, okay, or the router 2 here. So show IP OSPF interface gigabit Ethernet 0/0/0 here. Okay, now the state here is the Bdr and the priority is 1. So designated router is 3.3.3 that is connected to 192.168.1.3 here. Okay, so while R2 with router ID 2.2.2.2 at IP address 192.168.1.2 is the Bdr. Okay, so take note that on this line here, R2 has 2 adjacencies. One with the neighbor, okay, with router ID 1.1.1.1, which is R1, and the other with the DR, which is 3.3.3.3. Okay, so again, to verify the OSPF router role, we use the command show IP OSPF interface, and then you could type in the specific interface there. Okay. Now let us evaluate the router tree. Okay. So the output generated by R3 confirms that R3 is the DR with a default priority of 1. So as you can see here, so state DR priority is 1. Okay, so designated router is 3.3.3.3 connected at 192.168.1.3. While the BDR is R2 with router ID 2.2.2.2 at IPv4 address 192.168.1.2. Okay, so R3 has two adjacencies, one with neighbor with router ID 1.1.1.1, which is R1, and the other with the BDR, okay, so which is 2.2.2.2. Right? So again, the command to verify the OSPF router role is show IP OSPF interface command. All right. Next, how do we verify DR and BDR adjacencies? So to verify the OSPF version 2 adjacencies, we use the command show IP OSPF neighbor command. Okay, so as shown here, right, show IP OSPF neighbor command. Okay, so the state of neighbors in a multi-access networks can be as follows. It could be a full and then Drbddr. What does it mean? So this is a DR or BDR. Okay, so when you have SYN on your router, that the status or the adjacencies would be full Drbddr. This is a DR or BDR router that is fully adjacent with a non-DR or BDR router. These two neighbors can exchange hello packets, updates, queries, replies, and acknowledgements. Okay, so the next one would be full DR. So the router is actually adjacent with the indicated DR neighbor. So these two neighbors can exchange hello packets, updates, queries, replies, and acknowledgement. Also, the next one is full BDR. So the router is fully adjacent with the indicated BDR neighbor. Okay, so these two routers or neighbors can exchange hello packets, updates, queries, replies, and acknowledgement. All right. So next would be a two-way Drbddr. So the non-DR or BDR router has a neighbor relationship with another non-DR or BDR router. So these two neighbors can exchange hello packets. Okay. Now the normal state of an OSPF router is usually full. If a router is stuck in another state, it is an indication that there are problems in forming adjacencies. So the only exception to this is the two-way state, which is normal in a multi-access broadcast network. For examples, so Drbddrs will form a two-way neighbor adjacency with any Drbddrs that join the network. So when this happens, the neighbor state displays a two-way Drbddr. Okay? All right. So next would be R1 adjacencies. So the output generated by R1 confirms that, okay, R1 has adjacencies with the following routers. Okay, so that would be R2 with router ID 2.2.2.2. This is in full state, and the role of R2 is BDR. All right. Next would be with R3. That would be with router ID 3.3.3.3. Okay, so this is in full state, and the role of R3 is DR. Okay, now let us evaluate also the adjacencies on R2. Okay, so show IP OSPF neighbor. As you can see here, R1 with router ID 1.1.1.1, okay, is in full state, okay, and R1 is neither DR or nor BDR. So take note that R1 is a Drbddr, right? Okay. So next, R3 with router ID 3.3.3.3 is in full state, okay, and the role of R3 is DR. All right. Now let us evaluate also R3 adjacencies. So show IP OSPF neighbor here. Okay. Now the output generated by R3 confirms that R3 has adjacencies with the following routers. So 1.1.1.1, that's R1. Okay, R1 router ID is in full state. Okay. And R1 is neither the Dr nor the Bdr. R1 is a Drbddr. And then R2 with router ID 2.2.2.2 is in full state, and the role of R2 is Bdr. All right. Okay, so let's talk about the Dr-Bdr election process. So how do the Dr and Bdr get elected? Okay, so the OSPFv2 and Bdr election decision is based on the following criteria in sequential order. Right? So first, the routers in the network elect the router with the highest interface priority as the Dr. So the router with the second highest interface priority is elected as a Bdr. The priority can be configured to be any number between 0 to 255. So if the interface priority is set to 0, that interface cannot be elected as Dr nor Bdr. So the default priority of the multi-access broadcast interface is 1. So therefore, unless otherwise configured, all routers have an equal priority value and must rely on another tie-breaking method during the Dr and Bdr election. Okay? Now, the second one would be if the interface, okay, priorities are equal, then the router with the highest router ID is elected as the Dr. Now, the router with the second highest router ID is the Bdr. Recall that the router ID is determined in one of the following three ways, right? Just remember that. So the router ID can be manually configured, okay? So if no router ID are configured, the router ID is determined by the highest loopback IPv4 address. But then again, if there is no loopback interfaces configured, the router ID is determined by the highest active IPv4 addresses. All right. Okay, so let's have the default Dr-Bdr election process. Now, in the figure here, all Ethernet router interfaces have a default priority of 1. Okay, so as a result, based on the selection criteria listed above, the Ospf Router Id is used to elect the Dr and Bdr. So R3 here with the highest router ID becomes the Dr. So take note that the router ID here is 3.3.3.3. Okay, and R2 with the second highest router ID becomes a Bdr. Now the Dr and Bdr election process takes place as soon as the first router with an OSPF enabled interface is active on the multi-access network. So this can happen when the pre-configured OSPF routers are powered on, or when the OSPF is activated on the interface. The election process only takes a few seconds. So if all of the routers on the multi-access network have not finished booting, it is possible that a router with a lower router ID becomes the Dr. Okay? Now, OSPFv2 and Bdr elections are not preemptive. If a new router with a higher priority or higher router ID is added to the network after the Dr and Bdr election, the newly added router does not take over the Dr or Bdr role. Okay, so this is because those roles have already been assigned. Now, the addition of the new router does not initiate a new election process. All right? Okay, so Dr failure and recovery. So after the Dr is elected, it remains the Dr until one of the following events occurs. Right? So first, Dr fails. Okay? The second would be the OSPF process on the Dr fails or is stopped. And then third, the multi-access interface on the DR fails or is shut down. So if the DR fails, the Bdr is automatically promoted to a DR role. This is the case even if another Drbddr with a higher priority or router ID is added to the network after the initial Dr/Bdr election. However, after a Bdr is promoted to a Dr, a new Bdr election occurs and the Drbddr with the highest priority or router ID is elected as the new Bdr. Okay, so that's how it goes. Next, so in this example here, okay, on this illustration, okay, so R3 fails. Remember that R3 is our DR, right? So in this scenario, the current DR, which is R3, fails. So therefore, the pre-selected Bdr, which is R2, assumes the role of the DR. Subsequently, okay, an election is held to choose a new Bdr. Because R1 is the only Drbddr, it is elected as the Bdr. All right? Okay, so what will happen if R3 rejoins the network? Now, in this scenario, R3 has rejoined the network after several minutes of being unavailable. Okay, so because the DR and Bdr already exist, R3 does not take over either role. So instead, it becomes a Drbddr. All right. Okay, so next, what would happen if R4 joins the network? Now, in this scenario, okay, a new router R4 with a higher router ID is added to the network. So R2, which is the DR, and R1, which is the Bdr, retain the DR and the Bdr roles. So R4 automatically becomes a Drbddr along with R3 here. Right? Okay, so what if R2 fails? Okay, in this scenario, R2 has failed. The Bdr, which is R1, automatically becomes the DR, and an election process selects R4 as the Bdr because it has the higher router ID. All right. Okay, so how about the IP OSPF priority command? Now, if the interface priorities are equal on all routers, the router with the highest router ID is selected, the DR. Now, it is possible to configure the router ID to manipulate the Dr/Bdr election. Okay, so however, this process only works if there is a stringent plan for setting the router ID on all the routers. So configuring the router ID can help control this. However, in a large networks, this can be cumbersome. Okay. Now, instead of relying on the router ID, it is better to control the election by setting the interface priorities. So this also allows a router to be the DR in one network and a Drbddr in another network. That's possible. Okay. Now, to set the priority of an interface, we use the command IPOSPF priority value, where value is from 0 to 255. Okay, so a value of 0 does not become a DR or a Bdr. A value of 1 to 255 on the interface makes it more likely that the router becomes DR or the Bdr. Okay. All right, so let us configure the OSPF priority. So the following example shows how to clear the OSPF process on R1. So clear IP OSPF process, okay, command that must be entered on R2 and R3 also, which is not shown on this diagram here. Notice the OSPF state information that is generated here. Okay, so see this? So there are some sort of notifications here. Adjacencies, all right, process 10, right? So from full to down, okay, interface down or detected. All right. Now, how do we configure OSPF priority? So in the topology, the IP OSPF priority command will be used to change the Dr and Bdr as follows. Okay. So R1 should be Dr and will be configured with a priority of 255. So take note that we can use numbers 0 to 255. But then 0, setting it to 0, so your router will not participate in the election process. All right. Now, setting it to the highest will ensure that R1 will become the Dr. Right? So R2 should be the Bdr and will be left with a default priority of 1. And maybe on R3, okay, R3 should never be a Dr or Bdr and will be configured with a priority of 0. Okay? Now, change the R1 G00 interface priority from 1 to 255. Okay? And change the R3 G000 interface priority from 1 to 0. All right? Okay, so let's go to the next section. So modifying a single area OSPF version 2. Now in here, on this section, let's talk about the Cisco Ospf Cost metric. So recall that a routing protocol uses a metric to determine the best path, okay, of a packet across the network. So a metric gives indication of the overhead that is required to send packets across certain interface. So OSPF uses cost as a metric. A lower cost indicates a better path than a higher cost. The Cisco cost of an interface is inversely proportional to the bandwidth of the interface. So therefore, a higher bandwidth indicates a lower cost. So the formula used to calculate the OSPF cost would be cost reference bandwidth divided by the interface bandwidth. Now the default reference bandwidth is 10 raised to 8. Okay, therefore the formula is cost, okay, so which is 10 raised to 8 BPS divided by the interface bandwidth in BPS also. Now refer to the table for a breakdown of cost calculation because the OSPF cost value must be an integer. So fast Ethernet, gigabit Ethernet, and 10 gig Ethernet or interfaces share the same cost. So to correct this situation, you can adjust the reference bandwidth with the auto cost reference bandwidth command on each of the OSPF router. So manually set the OSPF cost value with an IP OSPF cost command on necessary interfaces. All right. Now, this is the table that we are pertaining to in the previous slide. Okay. So basically, you just have to refer to this table. If you are using 10 Gbps or 10 G Ethernet, the cost is 1. All right. So also, gigabit Ethernet, fast Ethernet, and Ethernet. Okay. Same cost due to reference bandwidth. Okay, so which are all 1. All right. So you don't have to compute, just refer to this table here. Okay, so adjusting the reference bandwidth. So the cost value must be an integer. Okay, if something less than an integer is calculated, OSPF rounds up to the nearest integer. So therefore, the OSPF cost assigned to the gigabit Ethernet interface with a default reference bandwidth of 10 raised to 8 BPS would equal to 1 because the nearest integer for 0.1 is 0 instead of 1. All right, so that would be cost 10 raised to 8, okay, divided by the bandwidth, okay, so that would be equals to 1. So for this reason, all interfaces faster than fast Ethernet will have the same cost value of 1 as a fast Ethernet interface. So to assist OSPF in making the correct path determination, the reference bandwidth must be changed to a higher value to accommodate networks with links faster than 100 Mbps. Okay. Now, changing the reference bandwidth does not actually affect the bandwidth capacity of the link. So rather, it simply affects the calculation used to determine the metric. So to adjust the reference bandwidth, we use the command auto cost reference bandwidth. That is an Mbps router configuration command. All right, so here's the syntax. Okay. Now this command must be configured on every router in the OSPF domain. Notice that the value is expressed in Mbps. So therefore, to adjust the cost for gigabit Ethernet, we use the command auto cost reference bandwidth, right? 1000 for 10 gigabit Ethernet. Use the command auto cost reference bandwidth 10,000. All right. Okay, so whichever method is used, it is important to apply the configuration to all routers in the OSPF routing domain. So the table shows, all right, here, the OSPF cost if the reference bandwidth is adjusted to accommodate 10 Giga Ethernet or Gigabit Ethernet links. So the reference bandwidth should be adjusted anytime. There are links faster than fast Ethernet or 100 Mbps. Okay, so in here, if you are using 10 Gbps, 1. Okay, same thing with Giga Ethernet. Okay, so looking at this table, it's 10. Fast Ethernet is 100. And Gigabit Ethernet, or sorry, Ethernet 10 Mbps, okay, or the Ethernet alone is 1000. All right. Okay, so OSPF accumulates cost. So the cost of an OSPF route is the accumulated value from one router to the destination network, assuming the auto cost OSPF bandwidth, okay, so 10,000 command has been configured on all the 3 routers. Now the cost of the links between each router is now 10, right? Got cost, all of those are 10. Now the loopback interface have a default cost of 1 as shown in the figure. All right. Okay, so therefore, we can calculate the cost for each router to reach each network. So for example, the total cost for R1, okay, to reach 10.10.20, which is this one here, okay, is 11. So how did we get 11? Right? So that would be 10 plus 1, that is 11. So this is because the link on R2 cost, okay, that's what I'm saying, is 10. And the loopback default cost is 1. So 10 plus 1, that is 11. All right. So the routing table of R1 here, okay, in the figure confirms that the metric to reach R2 LAN is at cost 11. So see this? Metric 11. So if you use the show IP route, right, that's 110 over 11. So this pertains to the cost. Okay, so can we manually set OSPF cost value? Yeah. So OSPF cost values can be manipulated to influence the route chosen by OSPF. Now, for example, now in the current configuration, R1 is load balancing to 10.118/30. All right. So 10.118/30. Now in here. So how do we know that this is load balanced? Right, so you have 2 possible paths to get into that network. So it's either via 10.1.1.13 and 10.1.1.6. Okay, now it will send some traffic to R2 and some traffic to R3. Okay, so because we can see it on the routing table. All right, so if we are R1 on R1, so we could forward some traffic here and some traffic also in here to get to 10.1.1.8, which is the network between R2 and R3. Okay, so the administrator may want traffic to go through R2 and use R3 as a backup route, as what we did in static routing, right? So floating static route sort of, okay? In case the link R1 and R2 goes down, okay? So another reason to change the cost value is because other vendors may calculate OSPF in a different manner. So by manipulating the cost value, the administrator can make sure the route cost shared between OSPF multi-vendor routers are accurately reflected in the routing table. Now, to change the cost of value reported by the local OSPF router to another OSPF routers, we use the interface configuration command IP Ospf Cost value. Okay, this is to simulate gigabit Ethernet speeds. So in addition, we will change the cost of the link between R2, okay, and R3 to 30 so that this link is used as a backup link. All right, so in that case, so you're gonna have this, okay. So interface G001 IP Ospf Cost 30, and then interface Loopback 0 IP Ospf Cost 10. Right? Okay. Now, assuming OSPF cost for R2, okay, and R3 have been configured to match the topology in the figure or on this PowerPoint here. Okay, so the OSPF routes for R1 would have the following cost values. So notice that R1 is no longer load balancing to 10118. So you only have one path here, which is via 10116. Okay. So in fact, all routes going to R2 as desired by a network administrator. Okay. So also note that although using the IP OSPF cost command is the recommended method to manipulate the OSPF cost values, an administrator could also do this by using the interface configuration bandwidth kbps command. However, that would only work if all the routers are Cisco routers. Okay. Next, so test failover to backup route. So what happens if the link between R1 and R2 goes down? So we can simulate that by shutting down the gigabit Ethernet 000, right? And verifying that the routing table is updated to use R3 as the next hop router. So notice that R1 can now reach the 10114/30 network through R3 with a cost value of 50. All right, so that's 50 there. Okay, so next, modifying the single area OSPF version 2 hello packets interval. So as shown in the figure, OSPF version 2 hello packets are transmitted to multicast address 224005, all OSPF routers every 10 seconds. Okay, now this is the default timer on a multi-access and point-to-point networks. Take note that hello packets are not sent on a simulated LAN interfaces because those interfaces were set to passive by router configuration passive interface command earlier. Now, the dead interval is the period that the router waits to receive hello packet before declaring that the network is down. Now, if the dead interval expires before the routers receive the hello packet, OSPF removes that neighbor from the link state database or LSDB. Okay, now the router floods the LSDB with information about the down neighbor out all OSPF enabled interfaces. So Cisco uses a default of 4 times the interval or the hello interval. So this is 40 seconds on a multi-access and point-to-point networks. Right? Now, on a non-broadcast multi-access or NBMA networks, the default hello interval is 30 seconds and the default dead interval is 120 seconds. So NBMA networks are beyond the scope of this module. All right? Okay, so how do we verify hello and dead intervals? So the OSPF hello and dead intervals are configurable on a peer interface basis. So the OSPF interval must match or a neighbor adjacency does not occur. So to verify the currently configured OSPF version 2 interface intervals, we use the command show IP OSPF interface and then the interface. Okay. Now the gigabit Ethernet 0, 0, 0 here, hello and dead intervals are set to the default. So if you will observe here, it's 10 and 40. So the dead timer is 4 times the hello timer. All right. Now the show IP OSPF neighbor command. Okay, so we can use also this to see the dead time counting down from 40 seconds, as shown in the following example. By default, this value is refreshed every 10 seconds. Okay, when R1 receives a hello from the neighbor. Okay, so it may be desirable to change the OSPF timers so that routers detect network failures in less time. Now, doing this increases traffic, but sometimes the need for quick convergence is more important than extra traffic it creates. Okay, so take note that the hello and dead intervals are based on the best practices and should only be altered in a rare situation. Okay, so OSPF version 2 hello and dead intervals can be modified manually using the following interface configuration mode command. So you could use no IP OSPF hello interval and no IP OSPF dead interval commands to reset the intervals to their default, which are 10 and 40. Okay. Now, in the example, the hello interval of the link between R1 and R2 is changed to 5 seconds. Okay. We'll have there. So immediately after changing the hello interval, the Cisco iOS automatically modifies the dead interval to 4 times the hello interval. However, you can document a new dead interval in the configuration by manually setting it to 20 seconds as shown. Right? So as displayed in the highlighted OSPF version 2 adjacency here, okay, when the dead timer on R1 expires, R1 and R2 lose adjacencies. So the reason is because R1 and R2 must be configured with the same hello interval. So better, okay, so not configure this or not alter the default settings. Now we use the command show IP OSPF neighbor command on R1 to verify the neighbor adjacencies. So notice that only neighbor listed is the 3.3.3 here. Okay. See that? R3 router. And that R1 is no longer adjacent with 2.2.2.2 R2 neighbor. So beware of changing these timers. So ensure if you have changed that on one end, you have to do the same on the other end. Okay, so to restore adjacencies between R1 and R2, the R2 gigabit Ethernet 000 interface hello interval is set to 5 seconds. Okay, so as shown in the following example here, almost immediately the iOS displays a message that adjacency has been established with a state of full. Right? So verify the interface intervals using the show IP OSPF interface command. Okay. So notice that the hello time is 5 seconds and that the dead timer automatically set to 20 seconds. So instead of the default 40 seconds. All right. All right. So next section, let's talk about the default route propagation. Okay, so default route propagation. So propagate a default static route in OSPF version 2. So your network users will need to send packets out of your network to a non-OSPF network, such as the internet here. Okay. Now, this is where you will need to have a default static route that can use or that they can use. Now, in the topology, okay, so R2 is connected to the internet and should propagate a default route to R1 and R3. Now, the router connected to the internet is sometimes called the edge router or the gateway router. So however, in OSPF terminology, the router located between the OSPF routing domain and the non-OSPF network is called Autonomous System Boundary Router, or the ASBR. Okay? ASBR stands for Autonomous System Boundary Router. Okay? Now, how do we propagate a default route? So to propagate a default route, the edge router, which is R2 on the previous topology presented, must be configured with the following. Okay, so we could have a default static route using the IP route 0.0.0.0, 0.0.0.0. We have the option to use next hop IP address or the exit interface command, like what we did on the static route or the static routing. Okay, now the default information originate router configuration command. So this instructs R2 to be the source of the default route information and propagate the default static route in the OSPF updates. Now, in the following example, so R2 is configured with a loopback to simulate the connection to the internet. So something like interface loopback 1, right? So IP address 64.100.0.1.255.255.255.252. Then a default route is configured and propagated to all other OSPF routers in the routing domain. Okay, so the command is, okay, so default information originate. Now, when configuring a static route, best practice is to use the next hop IP address. However, when simulating a connection to the internet, there is no next hop IP address. So therefore, we use the exit interface instead. All right. Okay, so how do we verify the propagated default route? So you can verify the default route settings on R2 using the show IP route. Okay, so notice that the route source on R1 and R3 is OE2, right? You'll have this OE2. Okay, so signifying that it was learned using the OSPF version 2. Now the asterisk identifies this is a good candidate for the default route. The E2 designation identifies that it is an external route. Okay, the meaning of E1 and E2 is beyond the scope of this module. All right. Okay, so let's go to the next section. So verify single area OSPF version 2. Okay, so verify OSPF neighbors. So if you have configured a single area OSPF version 2, you will need to verify your configurations. Okay, this topic details the many commands that you can use to verify OSPF. So as you know, the following two commands are particularly useful for verifying routing. So these are, of course, the show IP interface brief. Okay, this verifies that the desired interfaces are active with the correct IP addressing. So the next one would be show IP route. This verifies that the routing table contains all the expected routes. Now, additional commands for determining that OSPF is operating as expected include the following. So you can use show IP OSPF neighbor, show IP protocols, show IP OSPF, right? Or the show IP OSPF interface command. Okay? Okay, so how do we verify OSPF neighbors? So we use the command show IP OSPF neighbor command to verify that the router has formed an adjacency with its neighboring routers. Now, if the router ID of the neighboring router is not displayed or it does not show as being in the state of full, the two routers have not formed an OSPF version 2 adjacencies. Okay? Now, if two routers do not establish adjacency, link state information is not exchanged. So incomplete LSDBs can cause inaccurate SPF trees and routing tables. So routes to destination networks may not exist or may not be the most optimum path. So take note that a non-DR or Bdr router that has a neighbor relationship with another non-DR or Bdr router will display a two-way adjacency instead of full. Okay, now for each neighbor, So this command displays the following. So you've got the neighbor ID, okay? So this is the router ID of the neighboring router. You also have pri, okay? So this is the OSPF version 2 priority on the interface. So this value is assigned in the Dr and Vdr election. All right? So next would be state. This is the OSPF version 2 state of the interface. So full state means that the router and its neighbor have identical OSPF version 2 LSDBs. Now, on a multi-access network, such as the Ethernet, two routers that are adjacent may have their states displayed as two-way. The dash indicates that no Dr or Bdr is required because of the network type. Right? So the next one is a dead timer. Okay? So what is a dead timer? This is the amount of time remaining that the router waits to receive an OSPF version 2 hello packet from the neighbor. Okay? Before declaring the neighbor is down. Now, this value is reset when the interface receives a hello packet. Okay? So the next one would be address. This is the IPv4 address of the interface of the neighbor to which this router is directly connected. And the last one is interface. This is the interface on which this router has formed adjacency with the neighbor. Okay? So two routers may not form an OSPF version 2 adjacency if the following occurs. So first, the subnet masks do not match. Okay, so causing the routers to be on a separate networks. The OSPF version 2 hello and deaded timers do not match. The OSPF version 2 network types do not match. And there is a missing or incorrect OSPF version 2 network command. Okay? Now, next would be verify OSPF protocol settings. So we are using the command show IP protocols command as quickly or as a quick way to verify vital OSPF configuration information. Okay? So this includes the OSPF version 2 process ID, router ID, interfaces explicitly configured to advertise OSPF routes, the neighbors the router is receiving updates from, and the default administrative distance, which is 110 for OSPF. Okay? So the show IP protocols command is a quick way to verify vital OSPF configuration information. So this includes OSPF version 2 process ID, router ID, interfaces explicitly configured to advertise OSPF routes, the neighbors the router is receiving updates from, and the default administrative distance, which is 110 for OSPF. All right? So the default administrative distance for static is 1. Okay, so verify OSPF process information. So the show IP OSPF command can also be used to examine the OSPF version 2 process ID and router ID. So as shown in the following command output here. Okay, show IP OSPF. Okay, so you can see there. So routing process OSPF 10 with router ID 1111. So this command displays the OSPF version 2 area information and the last time the SPF algorithm was executed. Okay, so you can see here, SPF algorithm executed 4 times. All right. So next, the show IP OSPF interface command provides a detailed list of every OSPF version 2 enabled interface. Okay, so I specify an interface to display the settings of just the interface, as shown in the following output here for Gigabit Ethernet 0000. Okay, now this command shows the process ID, the router ID, okay, or the local router ID, the type of the network, which is point-to-point here, the cost, okay. Next would be Dr and Vdr information on multi-access links, which are not shown, and adjacent neighbors. Okay. Now, to get a quick summary of OSPF version 2 enabled interfaces, okay, so use the show IP OSPF interface brief. Okay, so as you see here, okay, so this command is useful for seeing the important information, including the following. So something like the interface or interfaces are participating in OSPF, networks that are being advertised, IP address, okay, mask, cost of each link, right? So network state and number of neighbors on each link. Okay, so we come to an end of this video lecture. It's a very long discussion. Okay, so thank you for watching and listening. Have a great day. Hope you learned something from this video lecture today.